Well, we missed one class, and I have a makeup, later this week. But anyway, yeah. I mean, is it okay? I mean, I don't know. It's 4 of you here, so. Okay, 5. Yeah, 5. So. Yeah. Mm-hmm.
So could you just find all the data points? Like, just find all the points?
Mm-hmm. Lots of points, yeah.
Lots of points for X's and Y's.
And then?
And then you couldn't just use a polyfit to those points?
Well, you have to decide on what degree polynomial. Okay. Well, it has to be, I don't know, 4th order. I mean, yeah, you can try 4th or a 5th order, but you see, if the points are equidistant, no, I mean, you do polyfit, but no. I think if you do polyfit, you run the risk of, of your fit not to go through those points. So. And it may have wide oscillations.
Because if you maybe split it to 2?
Yeah. Try both a polyfit and an interpolation. Try both. No. I mean, okay. The reason that came up is from the, we have a logo. Logo, and I don't remember who designed it. It was a good idea, but I think it was a bad implementation. What do I mean by that? Let me show you. So where is Where's our logo? Okay, anybody knows the logo I'm talking about?
The one right there on UCC.
No, it's the math. This math. Like there is a logo with a newsletter. Okay, it's gonna be in here. So let me. Wow, this is really bright. I like this. This one here. Okay, so when they did this, they basically said, okay, I'm gonna get something that resembles Pikes Peak. Okay.
That's giant now.
But but look at this. It's a 4th order polynomial. It doesn't have x squared. I don't know why. Anyway. So I just want a better thing to improve this logo. Yeah. No. But anyway, that was the idea. Okay, so let's let's start. I guess the thing already started. So. Okay, so I want to finish this discussion of Lyapunov stability and then talk about gradient in Hamiltonian systems. And I owe you something from last time, so let me just open that really quick. So we talked about equilibrium being stable, asymptotically stable, and this Lyapunov method we kind of try to apply on an example, on this example, right? X prime, whatever, right? Nonlinear system, where 0, 0 is the equilibrium, but it turns out it's not the only equilibrium. And then we started looking at, for this equilibrium, whether there are others or not, can we find a Lyapunov function and use that result, which we'll prove today, that if there is a Lyapunov function with those properties, then you have asymptotically stable equilibrium. Okay, and as I said, it's a hit or miss thing, right? You very rarely can just put your hand on a Lyapunov function because there's no recipe, right? So, but one thing that you might want to do is sort of try or start with this simple, quadratic functions like x squared plus y squared, or some constants with that, right? Multiplied to say x squared and some with y squared. And look at what the derivative of this Lyapunov function along solutions looks like, right? And we did a computation, and I think this is where we stopped. And I thought there was something wrong, but actually this works. So you can make this expression negative, okay? You just cannot make it negative in the whole plane. So obviously this would not be negative in the whole plane because of this terms, right? Okay. It's not obvious that this is always negative, right? It may actually be negative all the time, but I don't think it is. So what do? Well, the key is actually to look at the phase portrait. Okay, if you can do it. In 2 dimensions you can. That's why. Look at the phase portrait and look at some of the curves, right? And you see what happens. Okay, this is what the phase portrait looks like. And I don't know if this is in the plane, right? But does it give you like a 3rd dimension perspective? Does it give you some sort of a depth, sense of depth? The 3rd dimension? Well, as I said, it's like if you look from the top, from the airplane, and you kind of see this landscape, right? And if there is a dip, like if there's a valley here, right? And you can think of this as some sort of trajectories that go in that, like water pouring, sliding. All right. So, or it could be a peak, right? And then, but of course, the directions I think are in this direction. So it goes, let's say, it goes towards that point, right? So the picture shows that you do have a stable, asymptotically stable equilibrium, right? The only question is, we don't usually do proofs by pictures. We have to have some other tools. Like one tool was just linearize, right? Linearize and look. And linearization will have, well, obviously -2, -1. So it did what is indeed equilibrium. It was conjugate to a sink, right? So it is a sink. It's a conjugate sink for the linearization. So we're talking about this point, not this point. Okay, so that kind of that's an okay acceptable proof to say that it's asymptotically stable, but you don't know from that linearization how far you can go and still with your initial condition and still kind of be sucked in that sink. Okay, so this other method of Lyapunov functions is actually a good alternative, because so. What's the Lyapunov method saying? Is if you can find, so let me run this in the code so I can show you. Minus 2x minus y squared, right? And minus y minus x squared. I don't know, negative 2 to 2, less than negative 3 to 3. Now there's going to be a problem because it doesn't look, it not necessarily square, so I don't know, maybe like this. That'll be square. Okay, so that's how you get the okay, and then the phase border, and then you can look at equilibrium. This equilibrium, 0, 0, it has this eigenvalues negative 2, negative 1, so you can display the linearization, right? It does go in as you expect, okay? But again, this, it doesn't say how, in the original system, how far you can go from the origin.
Now, is that the difference between asymptotically stable and just stable?
No.
No,
asymptotically stable says the solutions go towards that point at infinity. Stable
from some limit.
From a neighborhood, yes.
From a neighborhood, right.
From a neighborhood of the point.
And if it's just stable, then it's from everywhere.
No, stable does not require that solution goes to even to that equilibrium. It just says it doesn't go away.
It goes to the area, to the neighborhood.
Stays in the neighborhood. Yeah, it's different. Yeah, but when it's asymptotically stable, the question is how big is this basin of attraction? Called is how far or in what region can I pick the initial conditions to go to that equilibrium? Well, so this is not saying that. This is not helping you with that. The linearization is not helping you with that, right? Because it only says if this looks like that in the neighborhood of, in a very small neighborhood of the. It doesn't say the size of the neighborhood. Okay. Now, if you just look at this. Would you be able to identify the entire basin of attraction for this equilibrium? Well, everything that I did so far goes to that point, right? So everything in this region is in that basin of attraction. In fact, you see that you can actually keep going until that's not in the basin of attraction, right? So there is actually this. It turns out there's another equilibrium here. And there is, how do you call these lines? Anybody remembers? So I have another equilibrium here, which obviously is not, right? It has a positive and a negative eigenvalue, so it's a saddle, right? And again, in the neighborhood of this point, you know what solutions look like, but how do we call this line, this curve? So basically, this is going to be the border of that basin of attraction, right? This point, and then that point. How do we call these two curves that go towards a saddle point? We talked about where do these curves correspond to with the linearization? Corresponds to the eigendirection of the stable of the eigenvalue with negative real part, right? So this and this, right? This is the direction of the negative eigenvalue, and this is the direction of the positive eigenvalue. Well, So we said this is conjugate to this, right? And this curve is basically the mapping of this eigendirection. And how do we call that curve? When we talked about conjugacy? Stable curve. And the other one would be the unstable curve, right? And these are real, I mean, these are never straight lines like they are in the linearization, right? This is a stable curve, or, higher dimension is called stable surface or stable manifold. But anyway, and this is just one dimension, stable curve. So the stable curve of this actually separates, see, the basin of attraction of this guy, right, from the rest. Now, so the basin of attraction is big, right? I mean, often is large, right? So the Lyapunov function is not going to tell you the entire one, but it's going to tell you like how far you can go in either direction, for instance, and still be absorbed by that sink. And I really don't know what I would do without people. So I really should give credit to this professor in Rice University, I think, that made this available. You can actually plot level curves of any function on top of this face portrait. So let's plot the level curves. What is a level curve of a function? Well, it's basically the points where that function is a constant, right? It's level. So if I take I want it's x and y. So I want the x squared plus y squared to be the function. So you just type it in here. And it should be x squared plus y squared. Okay? And you can actually let the computer decide like what levels to plot. Those will be concentric circles, right? Or you can control it by saying enter a vector of level values. So you can say plot, and this is the MATLAB notation, so you plot it as a vector. So you plot it as, I don't know, do you want the radius 1? Well, you can kind of see, right? The radius 1 looks like it's going to be in the basin of attraction. If you wanted a radius 2, then you'd have to do 4, right? Well, you kind of see that the radius 2, I think you might actually touch this, right? Well, let's see. I don't know. Let's try this. Let's try these 2 points and proceed. So it looks like it's included, right? In fact, doing the math, you can figure out what this point is, right? You can figure out what this other equilibrium. What was the other equilibrium? It was here. So. Yeah, you don't know if it's distance 2, but it's likely to be distance 2 from the other point, right? But anyway, you can do it with radicals with paper and figure out. So it looks like it's, yeah. So it looks like the basis of attraction includes the ball of radius 2. Okay. Okay. So now, how does this picture really help you proceed with that computation? You see, I mean, you can get really discouraged when you get an expression like this, because you don't know, I mean, it may not be, that may not be a Lyapunov function, so, you may never get this. But the point is that if you see the picture, then you can kind of ask yourself, if the arrows point inward in those level curves, right, from all sides, it means solutions, enter the level curves, and if it's just the radius, it means that it's going to decrease the radius. So it basically kind of confirms that yes, this is going to be decreasing. I mean, the derivative is going to be negative. So, but only in that region, not everywhere. So it's just a matter of how do you put things together to see that it's negative, right? And that's, I don't know, it's, again, hit or miss. So I think after several trials and errors, that's one way to see it. You know, the terms with x squared, put them together, the terms with y squared, put them together, and then say, well, this is always positive, right? X squared is always positive. So if this guy is negative, it's positive, then this term is going to be negative always, as long as this one, right? And you can see that, you know, this is positive in like a half plane, and this is positive in a half plane, right? So in this kind of region, it's clear that that expression is negative, right? Now you see that this region is not really represents the basin of attraction. So you really have to kind of say, well, radius, ball of radius 1 is in this region, so ball of radius 1 is in that basin of attraction, right? But to kind of go and say, well, ball of radius 2 is also in the basin of attraction, it is a lot trickier, and you'd have to go back to this expression and maybe group it differently, or figure out fancier ways of looking at the sign of this expression. Right? It's just a matter of looking at the sign of this quadratic, function of two variables to see where it's negative. Okay? And you may never be able to, you may never be able to find exactly where that expression is negative. But how do you do a sign chart for a function of two variables? You can plot it, basically. Plot it and see where it's above the plane, xy plane, and where it's below the xy plane, right? It's going to be some regions, right? And that, that's not, I didn't do that here yet, but, that would be a better kind of illustration of how the basin of attraction is. Okay? So there's a combination of computations done by hand, in addition with some plotting that are needed, basically, to get the biggest possible radius. Okay? So that was basically. Now, you see that there could be complications. Like, there could be that this table, this is the border of the basin of attraction. You see this curve here looks tangent to this radius, right? But maybe if you tweak, something in that equation, it will no longer be a tangent. It will be intersecting. So then it's going to be, basin of attraction will be less than, it will not include that ball of radius 2. And so then you may have to go and change v from being the Lyapunov function from being x squared plus y squared, maybe do ellipses, right, as the level curves. Anyway, so that's okay. Any questions on that? So try to use all the tools you have available to kind of do that. Now, let me just give you kind of a sketch of the proof of the Lyapunov. Sometimes I use y, sometimes I. So if I have I'm just going to remind you really quick, equilibrium, then, so if there exists L on some neighborhood of x star such that L is positive in in this neighborhood, and L is 0 at x at the equilibrium at 0, and it's positive outside. So you have a minimum. You have a strict minimum, and this is one. And the second one is that this is decreasing along curves, along solution curves. So it's derivative with respect to t of L of. Now, do you remember this notation too? Phi of t, that's the flow. Maybe we didn't use phi of t. Maybe we use phi of t and x naught. Yeah, that's what we use, right? That just means it's a solution starting at x naught at time t. I mean, at time 0, but evaluated at time t. Well, you take the derivative of this L function, which think of it as an altitude or something, right? In that landscape where the solution is moving, you evaluate the altitude, the value of the function, and if that's always, well, if that's not increasing, then x is stable, x star is stable. Okay, so, and if it's strictly decreasing, then it's asymptotically stable. Okay, so let's see that. Okay, so the proof for the stable is actually fairly easy. The key is in this level curves. So consider the level curves of L, meaning, so they're defined by this. It's basically points in the neighborhood where the Lyapunov function is defined, such that L of x is C. Okay, takes a value C. Okay. Well, if L is continuous and nice and differentiable, you can kind of show, and it has that property that it's, you know, this is the graph of L, right? It's like it has a minimum. Okay? So if this has a minimum, this means the level curves are basically going to be closed curves, right? They may not be round, they may be deformed, that are that contain the origin, the x star inside, right? And this is for one value of C, right? But what if for different value of C? So that will correspond to, for instance, this one here, right? If it's a smaller value of C, then this is going to be contained in that region. So it's going to be L minus L inverse, right? That's just notation for maybe C, let's say C1 and C2. So C1 less than C2, right? Means the level curve corresponding to C1 is inside, it's enclosed by the level curve corresponding to C2. Okay. Now that's a typical configuration, but it's not. You can have very weird type of level curves. I mean, one could be. I think there's a picture in the book that. So that's a typical configuration, but it's not a like universal configuration. I mean, it could happen that the level curve of corresponding to one level, like one value of the Lyapunov function, goes to infinity, right? I mean, it's like it's elongated this way and never, right? And then all of them are like this, right? Of course, you still have the minimum there, but it could, it doesn't have to be a closed curve. That's what I'm saying. Anyway, so if it is, think about x squared plus y squared or some combination of those quadratic terms. Okay? So, what do we do to show stability? That it's stability. We have to say, given any neighborhood of the point, we can find a possibly smaller neighborhood where initial conditions are picked at random, so that the solutions never escapes the original neighborhood that you picked, right? Okay, so let U or let O. Okay, let B of R be a neighborhood, a ball centered at X star of radius R. Okay. What we want to show is that need to show that there exists a smaller neighborhood. A smaller neighborhood such that initial conditions starting in the smaller neighborhood, so let's call it O1, imply that the solution stays in this ball. Okay? Does that mean stability for t greater than 0? That means stability, right? So I think the picture is still very useful here. So okay, so let's draw the picture here. So let's see. So this is X star. Now I have a ball of radius R, right? And I want to, let's make that bigger. Okay. So here's one way to do that. Okay, one way is to say the following: is that pick a level set contained in this ball. Okay. So as I said, the level sets, assuming they're closed, so this is not going to apply to that case that I mentioned earlier, where the level curve can actually be squeezing to infinity. All right. So let's pick a level curve that's inside of this a level set, right? So everything inside of this region actually has L that's smaller than this value C. Okay? And now take the neighborhood to be the inside of L inverse of C, which is the same as saying that this is L inverse of basically the values from 0 to c. So that's just a fancy way of saying this is the values of x for which L of x is less than or equal than c. Okay? You agree that's a neighborhood?
Can it be equal?
Yeah, also equal. It would be a closed neighborhood. It would include the boundary, right? Right? But I know that even the boundary is included in this BR. So that's okay. So this is going to be the neighborhood where I allow initial conditions to be picked. Right? So let's do that. So if I start with an initial condition in this, then that basically says that the value of L at that initial condition is at most C. Right? Well, but the fact that the derivative with respect to t of L of x of t is negative means that L of x of t is non-increasing, right? For t, from 0 to infinity. So I can conclude that the value of L at a later time is no greater than the value of L at the initial time, at the initial location. And this is less than C, right? So what this says is that x of t belongs to that neighborhood, right? Which is part of the bulb, if you want. Okay, so it basically says, that's just a fancy way of saying that, if you start on a level curve of this Lyapunov function, then you're going inward, right? You're never escaping. You may not go like. You may actually even let's see. Yeah. Well, you may the value of L doesn't increase, so you're not going outside, right? You may stay on the boundary. You may go around the boundary if you want, but you're going inward or you're staying tangent to the boundary, right? So that it's stable. You cannot start anywhere inside and escape outside. Okay? So stability is kind of an easy thing. What about asymptotic stability? So that's the Lyapunov asymptotic stability. Is saying that if this quantity is actually strictly less than 0 for any points in this neighborhood except the point, the equilibrium point, then the equilibrium point is more than stable. It's asymptotic listen. So not only that you stay in the neighborhood, but you're actually going towards that equilibrium. Okay, and the proof is a little bit it has to be somewhat different because it has to show the limit of this of a solution starting here actually approaches, right? So okay, so let x naught to be any point in this neighborhood, okay, where the Lyapunov function is defined. Okay? The first observation to make is that since the derivative of the Lyapunov function along solutions, in particular, in particular this solution, is strictly negative for t greater than 0. Okay? That's what we said has to be satisfied by the Lyapunov function. Well, the first thing to notice is that it means that x star is the only equilibrium in this. There's no other equilibrium where this is O, right? So in this neighborhood where the Lyapunov function exists, there's no other equilibrium. Why not? Because if there were an equilibrium, this guy would be independent of time, right? Starting at that initial condition, it would be independent of time, so the derivative would be 0. Okay? So this condition really excludes, if there are, there could be several equilibrium, like you saw in that picture, right? But this basically says the Lyapunov function cannot be, there cannot be a strict Lyapunov function defined everywhere, right? Because it doesn't accommodate equilibrium points. Okay? Alright, so that's one good thing. But also, for an arbitrary x naught, the trajectory x of t with t greater than 0 stays inside basically the level curve corresponding to L, right? Corresponding to what value of C? Well, the value where L started. If L started at, 5, then we know that along the solution, the L has decreased, right? So it means that it's in that level, inside of the level curve. Okay? Well, again, assuming the level curve doesn't escape to infinity, it means it's bounded. So it means that the omega limit set of x of t is inside of L inverse C. Okay, so here's the picture. I have now I'm focusing on, this is where x naught starts, right? So it starts on some level curve, right? Of course, this is the bigger O, right? That's the bigger O. And now I have L x naught is this, right? And I know that it's gonna decrease, so it's gonna go inwards, right? So because this goes inwards, what are the omega limits set? We talked about it last time. For a solution. No, for a solution. It's basically all possible points that are visited by the solution, right? So it's, so in other words, so the claim is that this omega limit set is x star. It's just one point. Because why is that enough? That basically says that that solution is attracted to that point. There is no other point that is visited. Okay, so this cannot really happen. This scenario cannot happen, that you can visit different points. But this is what we're trying to prove, is that it can only go towards that equilibrium, right? So how do we prove that? Well, we prove that by contradiction. So indeed, let's assume that z is omega limit point for this trajectory, and z is not, it's a point, but it's not that only equilibrium in that region. Okay, so what does it mean it's an omega limit point? It means that there exists a sequence of times for which x of tn approaches z. That's what it is to be omega limit set. It doesn't have to be for all times going towards that. It's just there are some times increasing going to infinity for which it gets closer and closer to z, right? Arbitrarily close to z. Okay? So let's see where's the contradiction. Well, here's the contradiction. It's all about what are the values of L. L has values that are decreasing, right? We know that. We know that the values of L are decreasing. So on one thing to say is that the values of L along these points, L is a continuous function. So if these points approach this point, then the values of L on these points will approach the value of L on that z. Okay? But the values of L on these points are actually, they're in decreasing fashion, right? These guys are decreasing because these are just, certain times in the evolution of the solution. So this, for any t, the L of x of t is decreasing, right? So certainly this is a sequence that is decreasing to this value. Okay. So there are some points, again I'm not saying it's the whole curve that is approaching, but there are some points going towards that point z. Okay? So now let's consider the curve that starts at z. Okay? Z itself has a curve, right? As an initial condition. I mean, maybe it doesn't go straightly towards this, but this has its own trajectory, right? So this was going this way, but now, so consider the solution of the curve, the solution curve that starts at z, and time, right? What do we know about this? Again, I think the pictures. We know that the L decreases along that particular solution as well. Right? So like after some time t, the value along this thing is going to be less than the value at z. Okay? So why is that how do you get a contradiction? So since L dot is strictly negative, it basically means that the value at t, the L at this is strictly less than z for any positive t, time t. Okay? And these guys were strictly positive than that. Okay? And they were tending to L of z. Okay? So where's the contradiction? At this point, except this solution curve may actually avoid all of these points. Right? I mean, this is just a discrete set of points going towards z. Right? This is actually going. Right. Well, all these discrete points will be above, right? Will be greater than. And then that trajectory is strictly less than the value, right? So the contradiction has to be made, the argument has to be made using that continuity of the dependence on the initial conditions. So that, let's see. I'm going to have to refer to this.
Can't you conclude that the L value of z is greater than L value at the equilibrium point, and therefore it can't stop there?
L value at z is
Greater than the L value at the equilibrium point.
Yes.
And therefore it can't stop at z.
well. That's what you're trying to show, but this is not saying it's stopping at z. It's saying that it visits z infinitely often. You see, if you had a periodic orbit, which is prohibited by the strict inequality, then then all of this would break. All of this argument would break. So okay, so I mean, here's the argument to make, is that you start at z, but you go sort of with you take a different time. Call it s, right? S of phi and z. Okay, so that's s at phi and z. And so let me change this to s. You'll see why it's important. Okay. And now, on the other hand, look at L of x of Tn plus s. Okay. What is L of x of Tn plus s? So s is just like a fixed positive number. Well, this is basically the same as L at phi s of x of Tn. Yes, I'm using the subscript. Remember that semigroup property that says, the time, where are you going to be at time t plus s? When you started at 0. Well, it's the same as where you are when you let s units of time pass after you've reached the place where you are when you were at t units of time from the initial time count. Okay. Well, the fact that this is continuous, so this flow is continuous. Remember that was the definition of our dynamical systems. The flow, this is continuous in xn, right? So this basically, it says that this is in the limit goes to L of phi s of z. Okay? But take a look at this. This guy is strictly less than L of z, right? According to what's above. So now you've gotten a sequence different from the original sequence of Tn's, on which L approaches something less than L of z. Okay? That cannot happen. Why it cannot happen? Well, if you were to plot L versus T, okay, L of x, right? We know that it starts somewhere and is decreasing, right? Well, on T1, T2, T3, yeah, I'm sorry, it shouldn't go to 0. It goes to some value, right? It's decreasing. So it goes to some limit, which is the, right? It has a limit. So if along this sequence it actually goes, we know it goes to L of z, right? It means along any other sequence it goes to the same limit. I don't know if that's, you can make that precise if you do. So it means that if I go by, I add s to each of them, right? Then the limit is still L of z. It cannot be below L of z, right? So it's a contradiction. Okay, I told you it's kind of a. Maybe you haven't seen this before, since if you haven't had analysis, but so this is a contradiction with the fact that L of x of t has to go to L of z. Okay, as t goes to infinity on every sequence. So, including on that sequence. So you cannot have something that goes to something, a limit, and then on a different sequence goes to a lower limit, because the function is decreasing. Okay, it's continuously decreasing. So it doesn't bounce. Okay. Tough argument, but. It shows basically that it kind of encapsulates the power of this stability statement or theorem. It says, just find me a Lyapunov function on which is strict, on which the values of L are strictly decreasing along trajectories. Conclusion is the equilibrium is asymptotically stable. Okay. Any questions? I mean, we can spend maybe more time on this, and I'm willing to spend more time because we'll revisit this thing when we talk about omega limit sets. Like, what kind of omega limit sets can we have? Remember what did I say last time? In the plane. If you have some sort of a bounding box where everything goes in and never goes out, right? But in that bounding box, I have 3 equilibrium and I have 2 periodic solutions. And I have a solution coming in, right? What's going to happen in the long term? It's going to have an omega limit set no matter what, right? And that omega limit set will be either one of the periodic orbits, so it's going to go like this, right? And it goes circles, or it's going to go towards an equilibrium, right? So that whole box, big box, is going to be sort of partitioned, right? In some regions that are attracted by one equilibrium, right? Another region attracted by another equilibrium. Maybe some saddle points. That's also a possibility. And then some periodic orbits will enclose, whatever is inside of that periodic orbit. It's never going to be touched by outside, right? Has to be inside, and inside there might be other equilibrium points. Okay, and this is only in the plane. Okay, so that's the Lyapunov stability. And let me say one more thing. That's called a. the strength of this method is that it kind of gives you the size of the basin of attraction of an equilibrium, right? So basin of attraction is the set of all initial conditions, right? Such that what? The solution as t goes to infinity approaches this point. You know, it's very good to be able to say something in words and write something in, you know, because it's just, you can trace things better. So, okay? So that's all it's saying, is the basin of attraction. And it can be, you know, half plane, like it can be infinite in some areas. Okay? But by the size, we mean it is like how far can you go in either direction? In all directions, right? So this is called the LaSalle, I think it's called LaSalle invariance principle. Invariance principle, which, again, just as a reference, the name, which basically says that if I have a Lyapunov function, and I don't know why they changed the letter, but defined on an open set containing the equilibrium point. Okay, so it's always is the same. We're really focusing at a dynamical system for which, you know, we single out an equilibrium point and we want to see how, you know, if it's asymptotically stable, how big is the basin of attraction. Okay, so if I have that Lyapunov function, so if this is a Lyapunov function for x star, so what are the conditions? L of x star is 0, L of x is positive for x different than x0, and L dot is, I think it doesn't require to be, yep, even strict, okay? And let P be a closed neighborhood of x star, included in this you know, set where the Lyapunov function exists, right? So, with what properties? Okay, which is positively invariant. Okay, what does that mean? It means anything that gets in there stays in there. Okay, for all, you know, for all positive times. If it's in that neighborhood at time 0, then it's in that neighborhood for all times. Okay, so it basically says if x not in that P, it means phi of t and x naught is in P for all positive t. Okay? So that's just like the level curves, the regions bounded by the level curves, right? Those are positively invariant. All right, and there is no entire solution, entire trajectory if you want, in P minus the equilibrium point, on which L is constant. What does that mean? So that basically says, well, first of all, there is no different equilibrium. There's no other equilibrium. So this neighborhood does not contain any other equilibrium. Because if it were another equilibrium, then that would, you know, that point would be the entire trajectory, right? It stays there, right? That's what it means to be equilibrium. And L would be constant on that. So that's right, avoided. Also, there are no periodic solutions on which L is constant, right? So it kind of avoids all the possible ways a solution not to go to X star, right? Then the conclusion is X star is asymptotically stable. And P is in the basin of attraction of X star. So if you can identify such a neighborhood for which there is no entire solution, entire trajectory on which L stays constant, then everything that starts in that P goes towards X star. Okay. Now let me not prove that because I'm not going to have time to talk about the other stuff. But the proof is similar to what the asymptotic stability was in that case. Okay, was in the the original stability result. I do really recommend you to go through that proof and try to see if you can understand it. Okay. And then, if not, I'm more than happy to go through it. But it has this idea of omega limit sets, of alpha limit sets. Alpha limit sets is what? Is if it has to do with this entire. Entire means go to positive and negative infinity. So if you start somewhere, it's like the p-plane does, right? You click a point, it shows the trajectory forward and trajectory backward. So. But how do you use this? Well, here's how you use it. For instance, if you use the pendulum as the, I mean, you can do this on every, but let's do the pendulum, which is, remember the pendulum? And let's change the friction. So there is some friction, small, but there is some friction. Okay, 0.5. So how would this thing tell us, like that result that we just wrote down? How would it tell us what is in the basin of attraction of let's focus on the equilibrium 0, 0. The other ones are just right translates. Right? This picture kind of repeats. Okay, so first of all, how do we know this is a asymptotic stable equilibrium? On the picture. Okay, that's proof by picture. Okay, any other way?
You can see that for a certain region, a ball around the equilibrium, all solutions tend inwards.
So, Lyapunov method, right? Okay. And the third one is the linearization, right? So, okay. So with linearization, we can see it's asymptotically stable. We cannot see how big the basin of attraction is, right? Proof by picture is not complete, right? It's helpful, but it's not complete. So let's try a Lyapunov function. Yeah?
For the ball, it could be any ball. Say you pick any ball, there exists open neighborhood inside of it.
For asymptotic stability?
Right.
You'd have to... Okay, this looks like square now.
I don't
Yeah.
necessarily understand what the ball thing is.
Well, it's just a level set of... If we are to see the x squared plus y squared, whether that's a Lyapunov function, that means the balls are the level sets. Okay? Now, when we talk about, if it's not a ball, if it's an ellipsoid, right? If it's an ellipse, then it's still a neighborhood. So in every neighborhood of a point, there is a ball. You can squeeze a ball. That's what it means to be a neighborhood. The neighborhood could be, kind kind of irregular, but it has to have a small but ball, ball of positive radius included in that neighborhood. That's the definition of neighborhood, which I didn't actually tell you what it is, but that's the definition, right? So referring to balls is basically enough. That's why the instability, it's enough to say, see if this works on the neighborhoods that are really circles. Okay? Now, the thing that you are saying is basically it's actually saying, let's see if we have a Lyapunov function. Okay, and it turns out that x squared plus y squared is not a good choice. I mean, okay, it is going to give you, it is going to be, you see, the whole thing is these guys are not, they're not like round, like it's not a spiral that's like, right? It's some sort of a skewed spiral. Okay, so it has more in one direction than in others. You see, and that really has to do with this, with the picture that, I don't know if I can fill this in, but you see, it's this. Well, it's the fact that it's nonlinear. It's not really a circle, right? But there is a better function, and I'm surprised that actually is even pre-programmed here. So, it basically says, take, they use omega and theta. That's x and y, right? Well, this is y. So use y squared minus 2 cosine of x. Okay, so let me just show this. So for nonlinear pendulum, well, what's a nonlinear pendulum? X prime equals y prime equals minus sine of x plus some constant times times y. Let me save this before it's. Yeah, I don't have it here. It's in the back. But I think it should last 5 minutes. I don't know. Just try to get it if you could. Okay. Excuse me. It's minus k, right? That's the friction term. Okay? So, Lyapunov function, and you'll see, I don't know if you'll see why, but let's consider it to be y squared over 2 plus cosine of x. Okay. Thank you. Okay. So I'll leave it as an exercise to show that this function. So how do you show that it's a Lyapunov function? You have to show this decreasing along solutions, right? So, that's a good question. Well, cosine of 0 is 1, so let's see. No, let's make sure it's the right one. Okay, so where is that? Yeah. You see that the fact that it has to be 0 is not so important. Let me see where it is at. Oh yeah, 1 minus cosine. Yeah, thank you. 1 minus. So it's okay, it's minus cosine. Okay, plus 1. Okay. This term is always positive or 0, right? And this term is always positive or 0. So the whole thing is positive. And it's 0 at the 0,0 equilibrium, right? And how do you compute L prime? Well, you just take the partials of this times x prime plus partial of this, is y prime and you'll end up with something that is negative, but not everywhere, only on a region, right? So the question is, how do you identify the region? Well, on P, that's P. So it's the x and y points for which this Lyapunov function is Lyapunov function is x and y is less than or equal than c, and y is, I'm sorry, x is less than pi. So the picture will look like this. This is negative pi, this is pi for x. So it's in this region, and then it's a level curve basically in that region. So what's the level curve? Well, you'd have to fix a value for c and look at, basically solve, I don't know, x cosine inverse or with y. I don't want to make a guess, but if I were, I would put, let's say this one here, okay? Saying that everything that starts inside is going to go towards 0, okay? Now, can you see that here? Well, you should. Negative pi to pi. So let's plot those level curves to see. Yeah, can you see it here? So maybe I'm going to change the negative pi to pi, negative 4 to 4, and this, I don't know, negative 2 to 2. It's hard to see, but you see the level curves are not exactly circles, but they are just, somewhat deformed. And the solutions that start on those regions stay in that region, right? And okay, and the key of this is, so do this picture on your own just to convince yourself. The key is that this guy is not always strictly less than 0. So you cannot just use that first statement that said if it's strictly less than 0, it's asymptotically stable, right? You have to go through this second invariance principle that I mentioned without proof to conclude that this is actually asymptotically stable, and it's telling you basically all these regions are in the basin of attraction. Now, what is the basin of attraction if you look at this picture closely? Well, this point is in the basin of attraction, right? So the basin of attraction is actually, I don't know, it's, yeah? So the global picture is actually more complicated, but what we're getting with the Lyapunov method is not so local, not a very local, right? It's not, we have to zoom in and, until we see it almost linear, right? It's not linearization. It's, you still have some, like you can enlarge this until you get to close to the other equilibrium points, right? As long as you don't, that's the invariance principle. You cannot have a region that has another equilibrium point in it. Okay? But you can blow it up as much as you can until you almost get to that point, right? And also you shouldn't have periodic solutions. Okay? I haven't done gradient systems, and I haven't done Hamiltonian systems. Is that okay for me to make up a lecture of that, and you going to watch it maybe over the weekend? Let's see, the homework has some of those questions, and I don't want to. Okay. So. There are three problems that ask about, one about gradient and one about Hamiltonian or gradient. So okay, I'll leave them on, and as I said, the lecture should kind of clarify what a gradient in Hamiltonian is. But if not, we can talk about it on Monday. So I'll leave it on for Monday. Try to do it after you watch the lecture. I should post the lecture Friday before noon. Okay. Yeah, I'll leave it on for Monday. So try to do as much as you can. If not, well, I just don't want to get into the exam date doing the homework. So, okay. But if you have questions about this gradient and Hamiltonian, maybe I'll give you an extra day or something.
So the exam will pick up on Monday and bring